In this video, we're going to review how to draw Lewis structures for molecules and polyatomic ions. It's essentially stuff you've seen in grade 11, just in some cases a bit more depth, but for the most part, what you've seen in grade 11 already. We're going to go through some examples and see the main steps, which are listed all on the left side here, and we'll do the examples on the right side over there. So the first example we'll start off with is a nice simple one. We'll do CF4. We'll do a Lewis structure for CF4. So our first step is to count the total number of valence electrons from all the atoms involved in the molecule or polyatomic ion, including the ion charge where applicable. Now in this case, there's no ion charge, so the next the little points here won't really matter, but I'll explain what those points there mean in a second. So let's start counting the number of valence electrons. Carbon is in group 14, so carbon has 4 valence electrons. And then fluorine is in group 17, so it has 7 valence electrons. What you need to remember is that there are 4 fluorines in this molecule, so you have to multiply that by 4, and that gives you 28 valence electrons to play with there. So in total, we have 32 valence electrons that we're going to be using to connect everything together. If this was a polyatomic ion, suppose we had an ion like CO3 2-, after our total count of valence electrons, we'd have to add 2 electrons. So for every negative charge you have to add 2 electrons to your total. For every positive charge you have, so let's say you had, for example, NH4 and then plus, for any positive charge you have, you need to deduct an electron from your total. So just remember that if ever you have a polyatomic ion. Now we have to decide where to place the atoms. So we have to find out what our central atom is going to be, the one in the middle, in other words, the middle atom. And we also have to figure out what the surrounding atoms are, the surrounding atoms. We often call surrounding atoms peripheral atoms on the periphery. They surround it, the peripheral atoms around the periphery. Typically, the central atom is pretty easy to spot. It's the one that there's less of. So in this case, carbon. But if you want a more chemistry-based answer to that, it's really the one that has the highest bonding capacity, which typically means the highest number of unpaired electrons, or also the least electronegative. That's usually how it's going to be. It might not always be like that, but typically that's how it is. But in this case, it's pretty straightforward. We just see carbon is the only carbon there, so that's probably going to be in the middle, and all the other atoms are going to be placed around the carbon, evenly around it. So we'll put C, F, 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 and F. So this is our step 2. So we placed our central atom and we placed our peripheral atoms around it. And next we're going to draw single bonds to the central atom. So we're going to connect each of the peripheral atoms to the central atom with single bonds. So 1, 2, 3, 4. And when we've done this, what we do is each of these single bonds, each one line, is going to represent 2 electrons. So what that means is that we've used up 2 electrons in each of the single bonds. So we're gonna subtract the number of electrons we've used from our total here. So since we had 4 single bonds, that's going to be 4 times 2. That's going to be 8. So we're going to take away 8 valence electrons from the total that we have. And that'll be 24 electrons left to play with. And so now that we have 24 electrons left, we're going to go and we're going to place the remaining electrons around the atoms. So we're going to place the remaining electrons around the atoms until they get a full octet. In other words, they have their complete valence shell, or 8 electrons. And generally, we do that for the outer atoms first, the peripheral atoms first. And then if there's any left, we can put them on the central atom. Just a little reminder, not all elements will require 8 electrons to be happy. For example, hydrogen just needs 2 electrons to be happy. So you can stop at that point. So let's go ahead and place our electrons. So we'll start, I'm going to draw these in a different color. You don't have to do that, but just to show you here. So I'll start with this fluorine. So we have 1, 2, 3, 4, 5, 6. Now it's happy because there's 6 of these electrons that are not in bonds. And then there's 2 electrons in the bond there because one line is 2 electrons. So now it has 8 total. And so we've removed 6 There's 18 left to place. Let's continue placing them, again, around the peripheral atom. So 1, 2, 3, 4, 5, 6, and then 2 in the line there. So that's 8 total. That one's happy. We've placed 6 more. So that's 12 valence electrons left. Let's go ahead and continue adding valence electrons. So 1, 2, 3, 4, 5, 6, plus 2 in the bond there. So that's happy. That's a stable octet. We've placed 6 more. So now we have 6 left to place, 6 valence electrons left. And what we're going to do is we're going to just finish placing the last few here. So 1, 2, 3, 4, 5, 6, plus 2 in the bond. That's 8. That one's happy. We've placed the last 6, 0 electrons left to place. And you might think, well, there's nothing to give carbon. And that's okay, because if you look at carbon, it is quite happy. The reason I say carbon is happy is because, let's just take a look here. Let's count a bit. It has 2 here, 2 here, 2 here, 2 here. It's happy. It has basically 4 from itself, and then it's sharing 1 with each of the fluorines. That's a total of 8. It has a stable octet at that point. And now what you've done is you've drawn the Lewis structure for CF4, following those rules there. Before we move on, I do want to label a couple terms to make sure you recall these terms from grade 11. So when you have electrons that are paired surrounding an atom, we call these lone pairs. Lone pairs. They're not in the bond. They're not in the bond. When electrons are in a bond being shared, they can be called shared pairs or bonded pairs. So they can be shared pairs or bonded pairs. And remember that if you have one single line, what that means is that you have 2 electrons in there, or 1 pair. And as we'll see later on, sometimes you might have more than 1 line. You might have 2 lines in between 2 atoms, or sometimes you might have 3 lines between 2 atoms. And so those are different types of bonds or number of electrons being shared between them. Let's do one more simple example following these rules here that just apply to these specific ones. And then afterwards, we'll do one that may have multiple bonds in it. So the example we'll do is, so this was our example 1. Now we'll do example number 2 here, following the same steps. We'll draw CH4. So we're going to count the number of valence electrons. We have 6 from carbon, and then 1 from hydrogen. But don't forget, there's 4 hydrogens, so that's going to be 4 total to play with. 6 plus 4 is 10. And actually, I already made a mistake. If you're thinking, wait, there's not 6 valence electrons for carbon. What are you talking about? You're right. It's in group 14. So there's 4 valence electrons for carbon. There we go. That's better. Times 4 gives us 4 valence electrons for hydrogen. And so that's a total of 8 valence electrons to play with. And so we're going to put our central atom in the middle. Again, the smallest amount is carbon here, so we can do that. C, put the H there, put the H there, put that H there, put this H there, and connect them all by single bonds to the central atom. In those single bonds, we have 2 electrons each, so 2 times 4 is 8. So we've already used up 8 valence electrons. That means there's nothing left to go place. And we have to check that our atoms are happy, though. So let's take a look at our hydrogen. Hydrogen only has 2 electrons in its valence shell now, because there's 2 in that bond here. So it is happy because hydrogen only has the first shell to fill, right? Remember, hydrogen only has the S subshell. So it's pretty happy with the 2 that it has there. 1 from carbon and then 1 from itself. Same with this hydrogen, same with this one, same with this one. It has its stable noble gas configuration like helium would. And carbon's also happy. It has 2, 2, 2, and 2 in those bonds there. And it's happy just as is. So there we drew the Lewis structure for CH4, for methane, using the rules. And so far, the 2 examples that we've seen are simply examples with single bonds. And just before we finish off, again, it's important to understand terminology. So if we look at lone pairs in the molecule CF4, you can count the number of lone pairs that there are. There's 3 over here. That's a lone pair, lone pair. 3 over here, 3 over here. Here, there's 3. Here, there's 3. And here, there's 3 total on each F. So that means in total, the number of lone pairs that we have are going to be 12 lone pairs. Or you can say 24 unbonded electrons or non-bonded electrons. How many bonded pairs do we have? 1, 2, 3, 4. We have 4 bonded pairs or shared pairs. In methane, CH4, there are no lone pairs. All the valence electrons are held up in bonds. And so we have 4 shared pairs, or we can call these as well single bonds. So in the next video, we're going to do some examples where we have molecules that may have something other than single bonds. They may have what we call multiple bonds, like double bonds or triple bonds between 2 or more, between 2 atoms.